Welcome to the Explainer. Today we're going to unpack a really brilliant wiring diagram that solves a classic, honestly, kind of frustrating electronics limitation, powering something big with something very, very small. Now, if you've ever tinkered with electronics, you know that matching your power supply to your component's needs is basically rule number one. But let's be real, sometimes you just don't have a massive battery pack on hand. And that is exactly where the low-voltage DC motor driver, using a D718 transistor, comes into play. We're going to look closely at a beautifully simple schematic that makes the impossible, well, possible. So let's start with a pretty provocative question. How can you possibly power a hefty 12-volt device using just a tiny household battery? Think about it. Normally, if you hook up a standard AA battery to a heavy 12-volt motor, crickets. Literally nothing happens. The motor just sits there, completely starved for power, because the electrical pressure simply isn't high enough to turn those heavy internal coils. Yet, as you'll see today, with the right arrangement of just a few basic components, we can essentially cheat that physics barrier and coax a high-power reaction out of a very low-power source. Okay, let's dive right into this schematic. Credited to taknomastr, by the way, which visually maps out the exact solution. What you're looking at here is the entire fully realized circuit, all on one screen. It's an elegant, honestly almost artistic layout that takes a tiny red battery at the bottom and uses this network of color-coded wires, a specialized coil, a resistor, and a transistor to wake up that big silver motor at the top. We're going to use this visual map as our guide throughout the rest of this explainer. Now, don't panic if this looks a little complicated at first glance. We're going to break this down into 4 really easy parts. 1, the voltage gap. 2, the core components. 3, tracing the power wires. And 4, the transistor control loop. All right, part 1, the voltage gap. 1.5 to 3.7 volts versus 12 volts. We are essentially trying to make a tiny stream do the work of a raging river. I mean, we've got a stark contrast here. On the input side of our equation, we have a low voltage 1.5 to 3.7 volt source. We're talking your everyday standard AA alkaline battery, or maybe a single lithium-ion cell. Then on the output side, we have a high voltage 12 volt requirement. That is the kind of power you usually reserve for car batteries, bulky wall adapters, or complex battery packs. Overcoming this immense discrepancy, that's the entire reason this specific wiring architecture exists in the first place. Moving on to part 2, meet the core components. Basically, our cast of characters. To bridge that massive voltage gap, we need to meet the components that make up this specific circuit. Think of these like actors in a play, right? Each one has a very specific role to ensure the final performance actually works. The diagram features exactly 5 physical elements. Up at the top, we have our target, the silver 12V motor. Over on the right, that black 3-pronged component is the D718 transistor. Dead center, marked by its colored bands, is a basic 1K resistor. On the left, wrapped in red wire around a white circular core, is a 12X/12X coil. And finally, anchoring the whole operation down at the bottom is our 1.5 to 3.7 volt red cylindrical battery. Now, what's genuinely fascinating about this setup is the specific inclusion of that 3-pin D718 transistor and the center-tapped 12X/12X coil. Without these 2 specific pieces, our little battery would be absolutely useless here. The coil is a toroid, meaning it's shaped like a donut, and it's wound with 2 sets of 12 turns of wire. That's what the 12X/12X actually means. The D718 transistor, meanwhile, acts like an incredibly fast electronic switch. Together, this dynamic duo is going to rapidly pulse our low voltage to create the momentum needed to drive that much larger motor. Okay, part 3, tracing the power wires, specifically the red and black paths. Let's actually trace how the power physically routes through these components, focusing on the primary red and black wires where the raw energy flows. By following the color coding, we can map out exactly where the current goes. Step 1. The black wire starts at the negative side of the battery, creating a common ground that connects to both the right pin of our transistor and the right terminal of the motor. Step 2. The red wire jumps from the positive battery terminal straight to the center of our circular coil. Step 3. From the right side of that coil, a red wire drops down to the middle pin of the transistor. And finally, step 4. The red wire from the left side of the coil travels all the way up to the left terminal of the motor. I want you to notice something crucial here. See how the red wire hits the center tap of the 12X/12X coil and effectively splits? It's sending one path all the way up to the motor and the other path down into the middle pin of the D718 transistor. This junction at the coil is essentially the beating heart of the circuit. It's channeling the continuous flow from the battery into 2 distinct routes that are going to interact with each other to step up our power capabilities. Which brings us to part 4, the transistor control loop, otherwise known as the purple wire. Finally, we have to look at the last remaining connection that ties the whole system together and actually forces it to start switching. If the coil is the heart, this is the brain of the operation, the purple wire path. This purple pathway is the control loop. It utilizes the 1K resistor to govern the behavior of the transistor. You can see it tapping off the left side of the coil, running down through the resistor, and plugging directly into the leftmost pin of the D718. That left pin, that's the trigger. The resistor ensures that just the exact right amount of signal gets through to tell the transistor when to open and close. And this just brilliantly illustrates how the circuit feeds a signal from the left side of the coil back into the left pin of the D718. It's a closed feedback loop. As energy moves through the coil, it sends this tiny little pulse down the purple wire through the resistor and triggers the transistor to briefly complete the circuit. This rapid-fire switching on and off, driven by the coil and controlled by this purple pathway, is exactly what dynamically manipulates the magnetic fields to squeeze out enough juice to spin a 12V motor. So the real takeaway here is that when you view the entire map on this final schematic, you see how these carefully routed red, black, and purple paths allow a tiny battery to spin up a heavy-duty motor. It isn't magic, folks. It's just incredibly smart routing. The continuous ground of the black wire, the split power delivery of the red wire through that custom toroid coil, and the precise timing of the purple feedback loop, they all work in perfect harmony. You're effectively building an electronic pump that takes little sips of low voltage and turns them into high-energy bursts. It really makes you wonder, right? With this clever wiring architecture, what other demanding devices could you potentially run off a simple low-voltage power supply? I mean, if a standard household battery can be reconfigured to drive a 12-volt motor using just a D718 transistor, a basic resistor, and a coil, the possibilities for portable low-power electronics are huge. It totally redefines what we consider a weak power source. Thank you so much for joining me on this explainer. Keep looking at those diagrams, keep tracing the wires, and keep learning. Catch you next time.